All right, we're going to continue with section 7.5, kinetic energy and the work-kinetic energy theorem. All right, when energy transfers across a boundary of a system, the amount of energy stored in the system changes. One of the possible results is that there's a system that the system changes its speed. So the figure, there's a mass with a force on it. And there's an initial velocity, there's a final velocity, and there's a delta x between them. So the figure shows a block of mass m moving through a displacement of delta x directed to the right under the action of a net force, which is also directed to the right. Now, Newton's second law says that the block moves with an acceleration of a. Acceleration is equal to the force divided by the mass, if you recall. So if it moves through a displacement of delta r, that is delta x times I hat, the I unit, the unit vector, the net work done on the block by the external force is as shown. The work is equal to x initial, the integral of x initial to x final of the sum of f dx. So we're breaking, the force is the same throughout, so we're breaking it into little dx units. So the result, now if we use Newton's second law and substitute ma for the sum of f and apply the chain rule, we'll get that the, in other words, the acceleration is dv dt, and dx dt is velocity. So we end up with the integral from v initial to v final of mass times velocity dv. Okay, now that's applying the chain rule. So the vi is the speed of the block at x equals xi at the beginning, and the vf is the speed at x final. That's v final. The equation is a general result of the work done by a net force on a particle of mass m. It's 1/2 mv final squared minus 1/2 mv initial squared. Okay, the kinetic energy represents the energy associated with motion of a particle. Kinetic energy is a scalar, and it has the same units as work. If you look at the mv squared, you have mass in kilograms, and m squared over second squared. So you have kilogram meters per second, so that's newtons, and then times another meter that's left over from the v squared, that's newton meters. So it's the same units, which is joules. You have kinetic energy is expressed in joules. Now the work equation states that work done on a particle by a net force acting on it is the change in kinetic energy of the particle. So the kinetic energy is equal to 1/2 mv squared. The final kinetic energy of the object is the initial kinetic energy plus the change in energy due to the net work done on it. All right. There it is. I'm sorry. One more click. The work is equal to the change in kinetic energy, K final minus K initial equals delta K. So let's, the equation comes from imagining doing work on a particle. Identify the particle as a system. We've increased the amount of energy stored in the system by doing work on it. Energy stored as kinetic energy is represented by motion of a system through space. We can also do work on a deformable system in which members of the system move with respect to one another. The equation is valid as long as the net work found by adding up works done by each force and adding them. The kinetic energy K of a system is equal to the sum of the kinetic energies of all members in the system. The important result is the work-kinetic energy theorem. When work is done on a system and the only change in the system is in the speed of its members, the net work done on the system equals the change in kinetic energy of the system. Work equals delta K, the change in kinetic energy. Okay. The work-kinetic energy theorem says that the kinetic energy of a system increases if the net work done on it is positive. The energy is being transferred into the system. The kinetic energy decreases if the net work is negative. That is, the energy is being transferred out of the system. All right. The work-kinetic energy theorem is also valid for systems that undergo change in rotational speed due to work done on the system, such as a windmill. The work done by the wind causes the rotational motion. Recall zero net work done when we let a spring push a block from x initial of minus x max to x final of x max. So the change in kinetic energy in the work-kinetic energy theorem only refers to initial and final configurations of the system. It doesn't depend on the path followed by any members of the system. The speed of the block equals 0 at both initial and final points of the motion. So the net work done on the block equals 0. Work can be considered a mechanism for transferring energy into a system when the external work done on the system results in a transfer of energy across the boundary of the system. And the result on the system is a change in kinetic energy. Now let's do a quick quiz. A dart is inserted into a spring-loaded dart gun by pushing the spring in by a distance x. For the next loading, the spring is compressed a distance 2x. How much faster does the second dart leave the gun compared with the first? Okay. It's twice as fast because the work is proportional to the square of the compression distance, and the kinetic energy is proportional to the square of the speed, v. Doubling the compression distance doubles the speed. Now if you're listening to this, I'm going to assign this as an extra point assignment. If you can come up with the equation using work 1 is equal to 1/2 kx1 squared, and the kinetic energy 1 is 1/2 mv squared, and then you use W2 equals 1/2 kx2 squared, and the kinetic energy 2 is equal to 1/2 mv2 squared. Substitute 2x1 equals x2 and see if you can come up with the equation as to why it's doubled. Extra points for anyone that's listening. All right, let's look at an example. Okay, a 6 kilogram block initially at rest is pulled to the right along a frictionless horizontal surface by a constant horizontal force of magnitude 12 newtons. Find the block's speed after it has moved through a horizontal distance of 3.0 meters. Now, we have the ability to find this out using our old equations of motion, in which V final squared equals V initial squared plus 2a delta x. And so we can, the V initial, remember the block is initially at rest, so V initial is equal to 0. And we know the acceleration from 12 newtons divided by 6 kilograms, it's 2 meters per second. So if you work it out, the velocity is equal to the square root of 2 times the acceleration, 2 meters per second times 3 meters. And if you work that out, it's 3.46 meters per second. So we have the ability to get this answer just from the equations of motion that we've already learned in the first few chapters. But we're going to use the kinetic energy work theorem. So let's get started with that. The net external force acting on the block is the horizontal 12 Newton force. We use the work-kinetic energy theorem for the block, noting that its initial kinetic energy is 0. We solve for Vf and use the equation for the work done on the block by F. So Vf is equal to the square root of 2 times the external work divided by the mass. So that's equal to 2 times the force times delta x. Work is equal to force times distance divided by the mass. Now let's substitute the numerical values. 2 times 12 newtons times 3 meters divided by 6 kilograms. You get an answer of 3.5 meters per second. You should solve this problem again by modeling the block as a particle under a net force to find its acceleration, and then as a particle under a constant acceleration to find its final velocity. In Chapter 8, we will see that the energy procedure followed above is an example of the analysis model of the non-isolated system. Now, suppose the magnitude of the force in this example is doubled to F prime equals delta F. The 6 kilogram block accelerates to 3.5 meters per second due to this applied force while moving through a displacement of delta X prime. How does the displacement delta X prime compare with the original displacement delta X? Well, if we pull harder, the block should accelerate to a given speed in a shorter distance. So we expect that delta X prime is less than delta X. In both cases, the block experiences the same change in kinetic energy. So we see that delta X prime is less than delta X because we're moving it, is more force, more acceleration, so the delta X is shorter to get for increased applied force. Mathematically, from the work-kinetic energy theorem, we find that the external work is equal to F prime delta X prime equals delta K, the change in kinetic energy, which is equal to F delta X. In other words, it's the same. So it doesn't depend on the force. Let's solve for delta X, and we'll see that F divided by F prime delta X equals F divided by 2F delta X equals 1/2 delta X. So the distance is shorter as suggested by our conceptual argument. Okay, now let's look at a problem. A man wishes to load a refrigerator onto a truck using a ramp at angle theta as shown in the figure. He claims that less work would be required to load the truck if the length L of the ramp were increased so that the angle theta would be smaller. Is this claim valid? Well, let's suppose the refrigerator is wheeled on a hand truck up the ramp at a constant speed. In this case, for the system of the refrigerator and the hand truck, delta K equals 0. The normal force exerted by the ramp on the system is directed at 90 degrees to the displacement of its point of application, and so does no work on the system. Because delta K is equal to 0, the work-kinetic energy theorem applied to the refrigerator gives work external is equal to work done by the man plus the work done by gravity equals 0. The work done by the gravitational force equals the product of the weight, mg, of the system, the distance L through which the refrigerator is displaced, and the cosine theta plus 90 degrees. Therefore, the work by the man is equal to the minus work of the gravity equals minus mg L cosine theta plus 90 equals mg times L sine theta equals mgh. L sine theta is the height of the ramp of the truck. Therefore, the man must do the same amount of work, mgh, on the system, regardless of the length of the ramp. The work depends only on the height of the ramp. Although less force is required with a longer ramp, the point of application of that force moves through a greater displacement. Okay, this ends our discussion. Let's see. Oh, so the answer is no. Is his claim valid? The answer is no. This ends our discussion of the work-kinetic energy theorem. Next, we will discuss section 7.6, potential energy of a system.